slide.
Hey y'all, welcome back. So today we're going to continue talking about vectors. Specifically, we're going to talk about how to multiply vectors. Now surprisingly, there's actually two ways to multiply vectors. One is called a dot product and the other way is called a cross product. And today we're just going to be focusing on the dot product. Now what's kind of weird is when you multiply vectors with a dot product, you actually end up with a scalar. You just end up with a single number. And what that number tells us is essentially how much force or how much of the force vector is applied in the direction of the motion vector. And let me try to explain what I mean by that. So let's say you have two vectors, A and B, shown here. If the vector forms a line, like A, and a line segment is dropped down from B to that line, you form a right triangle here. And when you multiply two vectors with a dot product, essentially what you're doing is you're multiplying this distance right here by this distance right here. So the distance from where the initial point is to this little point right here where sort of like the shadow of B ends. Okay, let me show you, let me go into a little bit more detail here. So what I'm calling this distance right here is kind of like the shadow of B on A. What I mean by that is if you were to drop down a line perpendicular to the line that the first vector lies on, this distance or this side of this right triangle is what I'm calling the shadow. So like from here to here. And if I multiply this value by this value, I'm going to get the dot product. If the two vectors are pointed in opposite directions, like they're down here, then you're going to end up with a negative product because the two directions, they're going in opposite directions. So you can think of this length as like a positive length and this length as a negative length. So there's actually a couple of ways that we can actually compute the dot product. As you might suspect, you could just find these two lengths and multiply them together, but it's actually easier than that. Okay. The first method I think is a little bit more intuitive based on how I am explaining what the dot product actually is. It's the magnitude of A, okay, times the length of what I'm calling B's shadow over here. Now we can calculate this by finding the magnitude of B and then multiplying by the cosine of the angle measure. So same thing up here. The magnitude of B times the cosine of this angle measure here is going to give you this length. So this little formula here is one way how you can calculate it. And it looks like we've got some notational issues here. So let me just fix that real quick since I just noticed that. So we have vector A dot B, and this should be a little vector notation there. Anyway, so it's the magnitude of A times the magnitude of B times the cosine of the angle measure, where that angle measure, this theta, represents the angle between the two vectors. Now, this is going to take a lot of work, I think, to get that dot product. It does work, but there is a faster way of doing it. It's a little bit more convenient, I think, because you don't actually need to know the angles between the two vectors. This is something that we haven't really talked about how to do yet. Later on, we'll learn how to get that. But for now, we really don't have a way of computing this angle measure outside of, finding the direction angle of A and B and subtracting them. So this formula right up here just takes a lot more work than what's really necessary. There is a faster way to do it, and to calculate this dot product, the easy way is to simply multiply the horizontal components, multiply the vertical components, and then add the two products together, and that'll give you the same number. I'm telling y'all, this way is way easier. It's a little bit of a shortcut here. So let's say we want to multiply like 2, 4 and 5, 7. So to get that, we're going to have 2 times 5. Let's make that a little bigger so you guys can read it a little bit easier. Okay, so 2 times 5, those are the two horizontal components. plus 4 times 7, which are the vertical components. Okay, maybe I'll use a different color just to really emphasize, you know, where this is coming from. So this is the 4 times 7. Here's the 2 times 5. Yeah, that green and black doesn't really look that different, but that's okay. Okay, so anyway, at this point, we're just going to compute this out. You can use a calculator. Probably don't need a calculator, to be quite honest. These numbers are pretty small. It's always a good idea to check your work, though. 5 times 2 is 10. 4 times 7 would be 28. And so we would add those together to get 38. So like I was saying before, it's, I think, not very intuitive that the solution is going to be a scalar, but it is. When you compute the dot product of two vectors, you do get a scalar. So let's talk about how you would do the dot product if you had three-dimensional vectors. If you have three-dimensional vectors, you're going to compute the dot product pretty much the same way. Actually, it's pretty much exactly the same way. The only catch here is you're going to have three products you're going to add up. So we will multiply our first components together. We will multiply our second components together. And we'll multiply, finally, our third components together and get our solution here. So we've got 1 times 9 plus 2 times -3 plus -3 times 5. Oops. And I'm just putting these negative numbers in parentheses just to kind of clean it up a little bit. So just make it a little easier to read, hopefully. So 1 times 9 is going to be 9. 2 times -3 is -6. And then -3 times 5 is -15. So we get 9 minus 6, which is 3. Minus 15 would be -12. I might just double check that just to make sure I don't have an error here. Let's see here. There we go. So yeah, let's just double check that. We got 1 times 9. Don't really need to do the 1 times, but 2 times -3 plus -3 times 5. Pretty sure we did it right, but let's just double check. Yep, okay, so we get -12. All is well. Let's go ahead and get rid of that. So that's going to be our answer for this one. You know, this is how you are going to multiply three-dimensional vectors using the dot product. It's just really, you're doing the same thing as you do up here. Okay, speaking of angle between two vectors, that's kind of what I was alluding to before. Okay, this theta in this formula is the angle between two vectors. So how do we calculate that if we know what the dot product is? And give me 1 second to fix up this notation. I'm actually going to pause the video so I can just knock this out without you having to sit through it. There we go. Okay, so basically if we want to find the angle between two vectors, then we're going to rearrange this formula that we had before and solve for theta. So this is really over here the formula you're going to want. This one down here. Okay, so it's the inverse cosine of the dot product divided by the product of the individual magnitudes. So I think this might make more sense if we actually use an example. Let's see here. So we've got 12, 3, and 4, -7. So we're going to have to come out and leave enough space for the -7. So just doing a rough sketch here just to kind of get an idea of what we're dealing with. We've got 12, 3, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 3. All right, so we got this vector right here. That's the 12, 3. And I'll just circle it so you can see. And then the 4, -7. would be over 4 down 7. So 1, 2, 3, 4, 5, 6, 7. And what we're asking for is this angle in between. So we're looking for this angle. That's going to be our theta. And really, as long as you know how to calculate the magnitudes and you know how to find a dot product, the rest of this you're just going to put in the calculator. So theta here is going to equal the inverse cosine of the dot product of these. So the dot product of these two vectors would be 12 times 4 plus 3 times negative 7. And then we need to find the magnitude separately. So remember that from last time, and if you want more explanation, you can go back to our last video. But to find the magnitude of a vector, you're going to use the Pythagorean theorem. So we'll do the square root of 12 squared plus 3 squared. And that'll be the magnitude of vector A, okay, or whatever the first vector is. And then we'll say times the magnitude of the second vector. So that would be the square root of 4 squared plus negative 7 squared. And so here is the long setup. I might make this a little smaller so we can actually fit everything that we need to fit here. So as long as you could put all that in your calculator, you should be good to go. Oops. Oh boy. There we go. What I'll do here is just kind of simplify piece by piece. Like let's find the, let's start with the dot product. So I'm going to pull up my calculator. Let's move this over a little bit. And we're going to do the numerator first, which is the dot product of A and B. So 12 times 4 plus 3 times negative 7, and we get 27. So the numerator up here is going to be 27. The square root of 12 squared plus 3 squared, I don't know if that's going to be a perfect square, so I'm just going to leave the square root there momentarily. And if it happens to be a perfect square, we'll deal with it then. It does not. So we're just going to leave it as root 153. That's the magnitude of the vector 12, 3. And then the magnitude of 4 and negative 7 would be 4 squared plus negative 7 squared. Just to save some time, you could just do 7 squared. It's going to be positive either way. So, so we get root 65. Okay. So this is going to be a little bit easier for us to type into the calculator. I would not advise you type in this whole thing. There's just a lot of room for error there. If you simplify it a little bit, you know, it can make things go a little bit more smoothly. So at this point, let's go ahead and do that. I'm going to make sure I'm in degrees. So change that to degrees. And we want the inverse cosine of this fraction, 27 divided by the square root of 153 times the square root of 65. And there you go. So before I hit enter here, let's take a quick look at my diagram. This is just a rough sketch, but if I'm looking at this, I'm trying to figure out, well, how many degrees is that? Looks like it's kind of close to 90, but it does look slightly acute. So if I had to just give a ballpark estimate with my crummy drawing here, I'm gonna go with like 80 degrees as like my estimate. So let's see if I'm right. Or, I mean, I'm not gonna be exactly right, but hopefully I'm not too far off. 74, okay. Not a, you know, it is acute, so I was right about that, but it was a little bit more acute than I was thinking. So that's good, it's still pretty close. It gives me a high degree of confidence that I got it right if my estimate is reasonably close to what I get in the calculator. So anyway, I'm gonna go ahead and write my answer here. And what was it, 72? Let me pull that back up. 74. So I'm going to get about 74 degrees. Okay, so that's how you find the angle between two vectors. The last thing we're going to talk about today is called an orthogonal vector. And basically, orthogonal vectors are vectors that intersect at a 90-degree angle. They basically mean perpendicular, but within the context of vectors. Okay? When the vectors are perpendicular, the angle between them is 90 degrees, right? And if the angle between them is 90 degrees, let me go back up to this formula. This right here, cosine of 90, is going to be 0. Okay? So if this number here is 0, 0 times anything is 0. So that means this whole side is 0, which means that the dot product is 0. So if we want to test to see if two vectors are perpendicular or orthogonal, we need to test to make sure that the dot product is 0. If the dot product is 0, then that means that we have a situation where we have cosine of 90, which will essentially prove that the two vectors are orthogonal. So if I've got these two, I want to show that they're orthogonal. Just to kind of give you a mental image of what's happening here, we've got one of these is going to be 4, 2. And the other one is 2, -4. Actually, are these even orthogonal? Yeah, they kind of look like it. Kind of looks like a 90-degree angle, right? Again, I'm just doing a rough sketch here, but looks like they're 90. But this is not proof here that it, looks kind of 90. We want to prove it by showing that the dot product is 0. So let's calculate the dot product. Basically, here's the proof. If this is what you need to know. Basically, if the dot product equals 0, then the vectors are orthogonal. So as long as we can show that, then we're good to go here. So here I've got 4, 2, dot 2, -4. And I want to show that this dot product is 0, and that will prove that they're orthogonal. So to calculate the dot product, we have 4 times 2, which is the product of the horizontal components, plus 2 times -4, which is the product of the vertical components, and we'll add those together. So 4 times 2 is 8. 2 times -4 is -8, and 8 minus 8 is 0. So what we've done is proved rather, that these two vectors are in fact orthogonal. All right, the last one here says find the value of t that would make the vectors orthogonal. Kind of the same setup, except we're going to be solving for a variable here. So we want like the equation we're going to set up here is that 1, t dot 6, -3. So the dot product of these needs to equal 0. So the dot product will be 1 times 6. Let's just delete the rest of this. So 1 times 6 plus t times -3. And that should equal 0. So this is how we're going to compute the dot product. 1 times 6 is 6. And -3 times t, we can rewrite that as -3t equals 0. And from here, we're just going to solve for t. So we're going to subtract 6 from both sides, which will leave me with -3t equals negative 6. And then we're going to divide both sides by negative 3. And that should give me t equals 2. All right, so just to kind of recap, kind of a short lesson today. We went over kind of what the dot product represents, how to calculate it with, I gave you 2 formulas, but kind of telling you to use this one. I mean, unless you know that, if you know the magnitudes and the angle between them, then you can just kind of plug these in. But let's say you don't, most of the time you won't, this formula is going to be a lot easier to deal with. We went over some examples on how to actually compute the dot product, and one little application here, or I guess 2 applications of the dot product. One is to find the angle between 2 vectors, and then the other one is how to show whether or not angles are orthogonal, which basically means perpendicular. So that's pretty much it for today. Y'all have a great day, and I'll see you next time.